Hello everybody, my name is Dimitrios Zorbas and I'm going to present you my work entitled ActLoRa Supporting Actuators in LoRaWAN. Before I go into details about the current work, I will give some background related to LoRa and LoRaWAN. LoRa is a proprietary spread spectrum modulation which trades data rate with sensitivity. This actually means that the longer the distance between an end device and the gateway, the higher the spreading factor, which is the parameter which controls the spread in the modulation and typically ranges from 7 to 12. The higher the spreading factor means better sensitivity, so longer range, but also lower data rate, which results in longer transmission times and in higher energy consumption. LoRaWAN is the open source protocol proposed by the LoRa Alliance for LoRa-enabled devices. It's based on an Aloha-based MAC, and it also provides some mechanisms like registration and security for LoRa-enabled devices. It uses 3 mandatory channels and 1 channel for additional channel for downlink, even though the providers can use more channels depending on the available spectrum and the regulations. A typical LoRaWAN architecture is this one. We have end devices which actually wake up and send uplinks to the network server, a back-end system, through a number of gateways here. The paper hypothesis is, since downlink communication is not allowed in LoRaWAN, except it is about acknowledgement and commands about the network, how can we enable device-to-device communications for actuating purposes in LoRaWAN? So how someone can send a direct message to another device without the intervention of one of the gateways. A typical example of such application is this one. Let's assume that we have a fire in a building and a device detects this fire. So it propagates the signal to one or more devices, actuators, which actually enable some evacuation doors, some fire extinguishers, or other alarms. Using the current LoRaWAN architecture, this is not possible unless we use a third-party network or a third-party protocol. So how can we do that in LoRaWAN, given the limited downlink availability of LoRaWAN devices? So what we want to achieve is to provide device-to-device communication for groups of devices consisting of one instigator, the device which instigates an alarm, and several actuators which actually put something in action. How can we do this? One way to do this is to use an overlay synchronized network only for this kind of devices, for these groups, and the rest of the devices can still use the typical LoRaWAN network. We want this synchronized network so that we wake up radios at the same time for the same group to transmit and receive data at the same time. Of course, this is not trivial. How can the devices can autonomously do that over LoRaWAN is very challenging. And how acknowledgements can send from one device to another. Also, another requirement is to have the same key material per group. However, we can easily solve this last requirement by storing a unique key for each of these groups on each of these nodes. As regards with the overlay time-slotted synchronized network, either LoRaWAN's Class B mode can be used or any other application layer for synchronization. In this work, we use a collision-free slot generation mechanism, which is called TS-LoRa, which actually autonomously assigns slots during the over-the-air activation through a pseudo-randomly generated device address, a unique address for each device in the network. This is done using the address prefix, which is the unique address prefix for each LoRaWAN network, the number of actuators here, and a randomly generated 25-bit number. All these constitute the device address. And then the slot is generated using a simple modulo operation in the hash function, which actually gives us the slot number. If this equation does not give us the slot number we want, let's say the slot 0, we need to regenerate another device address here using another random number, and do that until we get the slot number we want. For more details, we can check this paper. So, this process in ActLoRa is much more sophisticated. First of all, the network administrator needs to collect the dev EUIs of the actuators, something like MAC addresses, and set up the security keys for each of these groups. And then we have the two main parts. An instigator registers to the network over the air activation. During that process, it gets a unique device address which corresponds to a unique slot and satisfies the following criteria. The slot, as we saw in the previous slide, but also the device addresses of the actuators. So the device address of the actuators must give a slot number, which is the slot of the instigator plus the ID of each actuator in the group, and plus 1. We do that so in the end, the instigator in this frame format here will get, let's say, this slot, and the actuators will use the next successive slots for acknowledgements to the instigator. So each actuator I in the group registers to the network over the same process, and it gets a unique dev address I, which has been actually pre-computed during this step here, and corresponds to the instigator's slot and satisfies this criteria. The end devices, the actuators, can actually deduct the device address of the instigator using the reverse operation, which is an exclusive or very simple operation, and get also their slot here, the acknowledgement slot, in the frame using also some simple modulo operation. In the end, we'll end up with something like this. So we'll have an instigator followed by one or more actuators, and then another actuator somewhere here, another instigator somewhere here, and followed by a number of actuators, and so on. At the end of the frame, we have a beacon, which is used to synchronize the nodes with the gateway, and then this frame is repeated again and again. Performance evaluation. So in order to evaluate this work, this process, as regards with the computation cost, we want to check what is the execution time of these device address and slot, how long it takes to generate these device addresses and slots. So we have 100 to 1000 actuators, and we assign one instigator for 5 of each actuators. So each tuple consists of 1 plus 5 device addresses. As we can see here, the execution time is very low. The average execution time is almost constant and very low, about 10 milliseconds. The maximum execution time is also low. It never exceeds 0.3 seconds. On the right hand side is the simulation setup settings. You can see it here. The number of instigators is set to 10. this is constant fixed, and each instigator can have up to 5 actuators. Using a set of simulations, we want to check what is the impact of the Aloha part of the network on the synchronized network, because these two networks run actually over the same LoRaWAN network, so they coexist and they share the same channels. And these are some simulation results for 8 channels, uplink channels, and 3 uplink channels. As we can see here, the packet success rate for the synchronized network is very, very high, even when we have many nodes, so the impact, the probability of having a collision there is higher, it's still, the packet success rate is still high. The energy consumption is also constant. At the beginning we have higher energy consumption because of the synchronization, but as the number of nodes in the Aloha part increase, we have many collisions and retransmissions, so the energy consumption increases considerably. The same happens when we have 3 channels, even though in that case the probability of having a collision with the synchronized part of the network is higher. So as we can see here, the synchronized part of the network drops a bit more. We have also some experiments that are conducted in a residential building using 1 instigator and 2 actuators, using the TS-LoRa platform, which utilizes these PICOM low Pi 4 nodes. So using 1 instigator and 2 actuators for 3 different locations, here we change the location of the actuators while keeping fixed the location of the instigator for a short distance, for a medium range distance, and a long distance. As we can see here, the packet success rate is very high, and even if some packets are lost, is due to the path loss of the network. Okay, some open issues and future work here. An actuator currently is part only of 1 group. We need to investigate here what will happen if we have an application where we need to have actuators be part of multiple groups. Also, a channel hopping mechanism to avoid burst of collision in congested channels. Currently, the protocol supports only 1 single channel. And also how we can implement this over the synchronization of LoRaWAN Class B mode. That's it. Thank you for your attention. These are some links for the simulator and the implementation.